Okay, so let's have an example. So suppose that a bumpy jumping company hires you. You're given the task of predicting the velocity of a jumper as a function of time during the free fall part of the jump. Okay, so this information will be used as part of a larger analysis to determine the length or even required strength of the bungee cord for jumpers of different mass. You know from your studies of physics that the acceleration should be equal to the ratio of the force to the mass. So which is our Newton's second law of motion. So based on the insight and your knowledge of physics, you develop the following mathematical model for the rate of change of velocity with respect of time. So which is dB over dt is equal to g minus c of d over m multiplied by b squared. So again, b is equal to downward vertical velocity. T is the time in terms of seconds. G is the acceleration due to gravity, which is approximately 9.81 meter per second squared. And C of D is a lump drag coefficient. And then of course M is the jumper's mass. So the drag coefficient called lump because its magnitude depends on the factors such as the jumper's area and even the fluid density. So that is C of D. So because this is a differential equation, you know that calculus might be used to obtain an analytical, or even of course an exact solution for b as a function of t. Okay, so let's discuss how do we get that equation in the problem. So basically in the actual mathematical expression of your problem, so it can range from a simple algebraic relationship to large complicated sets of differential equations. So for example, on the basis of the observation on our problem, Newton formulated this second law of motion, which states that the time rate of change momentum of a body is equal to the resultant force acting on it. So the mathematical expression or even the model or the second law is well known as the popular one, which is an F is equal to ma. So where F against the net force acting on the body in terms of Newton. So getting of course A, so which is F is coming from the F is equal to ma. So we just simply divide both sides by m to get the A. So therefore A, or which is acceleration, is equal to F over m. So note that for this simple case, so there is no independent variable because there were not yet predicting how acceleration varies in time or even on the space. So for this case, a model can be derived by expressing this acceleration as the time rate of change of the velocity, which is dB over dt, and substituting it into the value of a, so which is a is dB over dt, is also equal to F over m. So where b again is the velocity in terms of meter per second. So that's the rate of the change of the velocity is equal of course to the net force acting on the body normalized to its mass. So if the net force is positive, basically the object will accelerate. If it is negative, the object will decelerate. So if the net force is zero, so of course our velocity will remain as a constant level. So next, we will express the net force in terms of measurable variables and parameters. So for a body falling within the vicinity of the Earth, so the net force is composed of two opposing forces, which is, we know that we have of course a downward pull of gravity and then of course the upward force of air resistance. So we just simply denote it as Fd as the downward, and then of course Fu is the upward force of air resistance. So therefore F is equal to F of D plus Fu. So if force in the downward direction is assigned a positive sign, so the second law can be used to formulate the force due to gravity. So therefore Fd, or the downward pull of gravity, is equal to mg. So g is the acceleration due to the gravity, which is 9.81 meter per second square. And then of course air resistance can be formulated in a variety of ways. So knowledge from the science of mechanics suggests that a good first approximation would be to assume that it's proportional to the square of the velocity. So which is our upward force. So Fu is equal to negative C of D multiplied by P squared. So again, C of D is the proportional constant called the lamp drag coefficient in terms of kilogram per meter. Thus, the greater the fall velocity, the greater the upward force due to air resistance. So we can combine all the equation from f of d plus f of u, which is our f. So therefore, dv over dt is equal to f over m. So therefore, we have dv over dt is equal to g minus c of d over m multiplied by b squared. So that equation is a model that relates the acceleration of a falling object to the forces acting on it. So it is a differential equation because it is written in terms of differential rate of change, so which is dv over dt, of the variable that we are interested in predicting. However, in contrast to the solution of Newton's second law of motion, so the exact solution of dv over dt, g minus cd over m multiplied by b squared, for the velocity of the jumper cannot be obtained using a simple or even an algebraic manipulation. Rather, more advanced techniques such as those of calculus must be applied to obtain an exact or even, of course, an analytical solution. Okay, so for example, the jumper is initial at rest, which is b0 at t is equal to 0. So again, calculus can be used to solve that equation for b of t square root of gm over cd tangent hyperbolic of g square root of g multiplied c of d over m multiplied by d. Okay? So, let's have an example of analytical solution to the bungee jumper problem. So, our problem statement. So, a bungee jumper with a mass of 68.1 kilogram leaps from a stationary hot air balloon. So, we have to use, of course, our b of t. So, to compute velocity for the first 12 seconds of free fall, so use a drag coefficient of 0.25 kilogram per meter and an acceleration to gravity which is a 9.81 meter per second squared. So inserting all the parameters into the equation, so b of t is equal to square root of quantity 9.81 multiplied by 68.1 all over 0.25 hypertangent hyperbolic square root of 0.25 multiplied by 9.81 over 68.1 of multiplied by t. So resulting of course, which is 651.6938 tangent hyperbolic 60.18977 multiplied by t. So again, that formula or that equation can be used to compute velocity as indicated in the table. So according to the model, the jumper accelerates rapidly. So a velocity of 49.4214 meter per seconds is attained after 10 seconds. Note also that after a sufficiently long time, a constant velocity called the terminal velocity of 51.6983 meter per second is reached. So this velocity is constant because the analytical solution for the bungee jumper problem as computed in our problem, okay, so velocity increases with time and approaches of course a terminal velocity.